Okay. All right, so divisibility rules. For each number, determine if it is divisible by 2, 3, 4, 5, 9, or 10, and list all that apply. And for these particular integers, they have associated rules. To find out if a whole number is divisible by 2, that is to say, a whole number is even, look in the units place or ones place and see if it has 0, 2, 4, 6, or 8. To find out if a whole number is divisible by 3 or is a multiple of 3, find the sum of the digits of the number, and if you obtain something which is on the 3 times table, then the original number itself was on the 3 times table. To find out if something is divisible by 4, that is a multiple of 4 or on the 4 times table, look at the last 2 digits and see if they are on the 4 times table. This divisibility rule makes sense because 100 is divisible by 4, and therefore the 4 times table will have a cycle of its final 2 digits every 25th multiple. So, for example, it will go 92, 96, 100, 100, and then it'll start all over again. 104, 108, 112, 116, 120, and so on. Divisibility by 5. That's as easy to check as divisibility by 2 when working in base 10, the decimal number system. Just look at the ones or units place value of the given number, and if it ends in a 0 or a 5, then it's a multiple of 5. It's divisible by 5. For divisibility by 9, it's similar to the divisibility by 3 rule. Find the sum of the digits of the whole number in question, and if you obtain the number that is on the 9 times table, then the original number was divisible by 9. And finally, for divisibility by 10, this is something everybody knows. If it ends in a 0, the whole number, then it is divisible by 10. And so now to apply those rules, to these given numbers. So 120 is divisible by 2 and 3 and 4 and 5. And is it divisible by 9? Well, no, because the digits do not add up to something on the 9 times table, but it is divisible by 10. Of course, I could factorize this and list out all of the divisors, but for now, I'm just applying divisibility rules. For 75, this is indeed divisible by 3, as the digits sum to 12, which is on the 3 times table. And it's divisible by 5, as it ends in 5. But not by 9, as its digits sum to 12, which is not on the 9 times table. And, of course, not by 10. For 918, the sum of the digits is 18, and therefore it's divisible by 3 and 9. If it's divisible by 9, this implies that it's divisible by 3. Of course, it's even, so it's divisible by 2. But is it divisible by 4? Well, we only need to look at the last 2 digits. 18 is not on the 4 times table, and therefore 918 is not divisible by 4. It's not divisible by 5 or 10. So really it's just 2, 3, and 9, which I'll put next to each other as a list. Okay. I will add to this list 6. And here's why and here's how. If something is divisible by 3 and it is even, then it is divisible by 6. That's a simple divisibility test for 6. As for the divisibility test for 8, one need only check the final 3 digits of the number in question. If the final 3 digits are a multiple of 8, then the entire number is a multiple of 8. So I will include 8 in the list as well. 7, however, is a lot trickier, and 1 is trivial. So really, there's a divisibility rule for all the numbers from 1 to 10 except for 7. And so I'll apply these to the numbers, to all the numbers going forward from here. So it's divisible by 1 and 2 and 3 and 4, as 36 is on the 4 times table, not 5. What about 6? Well, it's even and divisible by, oh, beg your pardon, it's not actually divisible by 3. Oops. Okay, that was a blunder. Okay, because it's not divisible by 3, we kick out 6. It's not divisible by 6. But is it divisible by 8? No, because 36 is not on the 8 times table. What about by 9? Well, adding the digits, we get 10, but we need not have done that check as it's not divisible by 3. And that's really it for 1036. For 1037, it's not divisible by 2, nor 3, nor 4, nor 5, nor 6, and nor 8, nor 9, nor 10. Not by any of them. But I'm curious if it's divisible by 7. So we jump to 700, and then we have 337 left. And then we go to 350, and then deduct 14, and we get 336. So this number here was divisible by 7, but this one was not. Now 4,806. Well, that's divisible by 1 and 2. And what about 3? Yes, indeed, 3. In fact, finding the sum of the digits, we get 18, and therefore it's also divisible by 9. By 4, no, because that's not a multiple of 4. By 5, no. By 6, well, yes, because it's even and divisible by 3. Once we see the 2 and the 3, we can instantly list 6. Is it divisible by 8? Well, we can look at the last 3 digits and we see 806. So that's not on the 8 times table, so 8, unfortunately, no, not. And then, of course, I'm curious about 7. So straight away, we jump to 4,900. And then we know that this is 94 below. And is 94 divisible by 7? No. And so I Our concluding answer is 1, 2, 3, 6, and 9. Next up, 11,205. The sum of the digits is 9. So straight away we can write 1, 3, and 9 right there. It's also on the 5 times table. Not on 6, not on 7, not on 8. But what, hold on just a second. Not on 6, and not on 8, and not on 10. But what about 7? I'm curious. So straight away, 7,000, which gives 4,205 left. 4,200, take that off, and we have 5 as a remainder. So no, it's not on the 7 times table. 98,010. Sum of the digits is 18. So 1, 2, 3, and 9. 5 also goes into it, and so does 10. Now what about 4? Well, the final 2 digits are not on the 4 times table, so no. What about 8? Last 3 digits are not on the 8 times table, so no. What about 6? Well, we already see a 2 and a 3, so 6 comes for free. And then, out of curiosity, I pursue 7. We take off 98,000, and we're left with 10, which is not on the 7 times table. So it's 1, 2, 3, 5, 6, 9, and 10. For 708, 1, 2, 3, and therefore 6. 4, indeed. 5, no. 7, we can instantly see no. 8, don't know yet. 9, we know not. 10, not. But what about 8? Well, is this on the 8 times table? So we jump to 800. We know that it's 92 below. Is 92 on the 8 times table? The answer is no. And so this is our final answer. 1, 2, 3, 4, 6. And last here for 3,195. 1, not 2, but 3. Add the digits. We get 18. Oh, so 3 and 9, they're included. 4, no. 5, yes. As you can see, a 5 here. 6, no, as it's not even. And neither does it apply to 8 or 10, but I'm curious about 7. So straight away, I jump to 2,800. Then we have 395 to go. Take off 350, then there's 45 to go, and that's not on the 7 times table. So it's 1, 3, 5, and 9. And I'm going to open up the answers on the other screen. So the first one correct. Next, good. Yeah, here's where I started to include 1 and all my other sort of divisibility rules. The fifth one, no, nothing. 1, 2, 3, 9. 1, 2, 3. Yep. Oh, whoa, hold on. Just a second now. Well, I got 18 from this, and that's on the 9 times table. So potentially one of their answers is actually wrong. Oh well. So they did get an answer wrong. 9 actually is a divisor of 3,195. See? Okay. Now, to identify each number as prime, composite, or neither. And if it is composite, I better provide proof of my claim. And there appear to be sort of like 12 questions. Interesting, cool. So for 1, the answer is neither. It's the unit, which is in a sort of privileged set all on its own. As for 2, yes, it's a prime. It's the only even prime, which makes it kind of odd. Get it? It's the first. "19 is indeed prime. It's P8, the 8th prime. 27 is composite. Three cubed. 51 is composite. 3 17s. 89 is prime. But which prime actually is it? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89. Therefore, it's the 24th prime. "91 is composite. 91 is 7 13s. And 121 is composite. It's the 11th square number. And so now let's list all the prime numbers between 10 and 30. So 11, 13, 17, 19, 23, 29, and not 31. Oops. Okay. Whenever there's a between A and B statement, there's always some ambiguity. Wait, do you mean the endpoints are included or excluded? But in this case, there's no ambiguity because 10 and 30 couldn't possibly be primes. And now to list all the composite numbers between 40 and 50. Now there is ambiguity. I will default to an inclusive between. So I shall say 40, 40, 42, 44, 45, 46, 48, 49, and 50, as the only primes between these bounds are 41, 43, and 47. But I have to justify that these are composites, don't I? Okay, 40 is 2 cubed times 5. 42 is 2 times 3 times 7. 44 is 2 squared times 11. 45 is 3 squared times 5. 46 is 2 times 23. 48 is 2 to the 4 times 3. 49 is 7 squared, and 50 is 2 times 5 squared. What is the first prime number greater than 50? And I say it's 53. My justification is the factorization of 51, the only other potential candidates or reasonable potential candidates, because 50 was just factorized as 2 times 5 squared, and 51 is 3/17, and 52 is obviously even, but I'll just factorize it anyhow. 52 is 2 squared times 13. What is the largest prime number less than 100? The answer is 97. As divisibility rules can be performed on 97 or by trial division. (97) is prime by trial division. And then I need to show that 98, 99, 98 and 99 are composite. 98, obviously even. Nonetheless, for thoroughness, I'll just show you that it's 2 times 7 squared. And 99, obviously a multiple of 3, but nonetheless, it's 3 squared times 11. And now let's check. Checking everything. Indeed. All right. Okay, this didn't put it on a new page, but that's all right. Write the prime factorization of each number and use exponential notation. I would be glad to. This is 2 squared times 7. 28 is 2 squared times 7. 48 is 2 to the 4 times 3. 16 times 3. 60 is 2 squared times 3 times 5. 100 is 2 squared times 5 squared. 81 is 3 to the 4. 98 is 2 times 7 squared. And 135 is, well, it's divisible by 5. So what? 5 times 27? So 3 cubed times 5. 250 being 10 times bigger than 25 would be 2 times 5 times 5 squared. In other words, 2 times 5 cubed. 315, it's obviously a multiple of 5. Double it and divide by 10 to find out which multiple of 5 it actually is. And upon doing so, we learn that it's the 63rd multiple of 5. And 63 is 3 squared times 7. So it's 3 squared times 5 times 7. 512, famously, is the 9th power of 2. And we check. Correct. All correct. All good. Great. Now to find the total number of divisors. Let's see. I'm pretty sure there was a nice notation. I want to learn that. All right. So it's called the divisor function. Divisor function is an arithmetic function related to the divisors of an integer. When referred to as the divisor function, it counts the number of divisors of an integer, including 1 and the number itself. It appears in a number of remarkable identities, including relationships on the Riemann zeta function and the Eisenstein series of modular forms. Divisor functions were studied by Ramanujan, who gave a number of important congruences and identities. These are treated separately in the article Ramanujan's sum. Let's see. The sum of positive divisors function sigma sub z of n for a real or complex number z is defined as the sum of the zth powers of the positive divisors of n. Let's go straight to examples. Oh, I see. Sigma sub 0 of 12 is the number of divisors of 12. Sigma sub 1 of 12 is the sum of all the divisors. Well, all right. Okay, so we'll apply it to 10. We know that has 4 divisors. And sigma sub 1 of n would be the sum of those divisors. So 1, add 2, add 5, add 10, which is 18. And sigma sub 2 of n will be the sum of the squares of the divisors, I guess. So 1, add 4, add 29, add 100. Did I calculate that right? 1 add 4, that makes 5. Oh, yes, of course it is. Yeah, okay. Interesting. Yes, that's true. Okay. Abundancy index. some of the proper divisors. Now, I don't know how to say that, so I'm going to go to Forvo, type it in, aliquot. Okay, so S is used exclusively for that. All right, so now to get on with the task. Find the total number of positive divisors for each number. So I'm going to write sigma 0 of 10 equals, well, 4. And sigma sub 0 of 16 would officially be 1 to the 0 plus 2 to the 0 plus 4 to the 0 plus 8 to the 0 plus 16 to the 0. But I already know ahead of time that the number of divisors is 5. So we just check for those first two, make sure that we're doing it right. And we are. Okay, wonderful. Okay, I'm just going to get used to the notation here. Now, for such teeny tiny numbers, I can list them. I can literally just list them out. 1, 2, 3, 5, 6, 10, 15, 30. So the answer is 8. And we check, and that's correct, and that's good. For 36, you start to feel some shaky ground, sigma sub 0 of 36, because you think, okay, 1, 2, 3, 4, 6, and then I start going back on myself, 9, 12, 18, 36, and you get 9. And you can sort of like think to yourself, well, it's a square number, so I know it's going to have an odd number of factors. But why do they keep dropping these hints here? Because for a given number whose prime factorization goes like this, these number of divisors would be k1 plus 1 times k2 plus 1 all the way up to kn plus 1. And you could even be needlessly formal and official about it and say I equals 1 to n ki plus 1. Like that, a finite product. So let's put it into action. It's really an overly complicated way of saying, in this case, all you do is just do 3 times 2. .45 must have 6 factors, and we can check it by hand. So its factors would be 1, 3, 5, 9, 15, and 45. Now for the rest, they don't tell you. So I should prime factorize it first. This is 2 to the 6, and therefore the number of divisors of 64 is 7. This is 2 to the 4 times 5, or if you want to be explicit, 5 to the 1, and therefore the sum of the divisors of 80 is 5 times 2, which is 10. You can list them all out if you want. It's a nice exercise to go up to the fifth divisor in ascending order, and then down to the 10th divisor, because they occur in those pairs. So it would be 1, 2, 4, 5, 8, and then down 10, 16, 20, 40, and 80. For 100, we prime factorize it as 2 squared times 5 squared. So the number of divisors is 3 times 3, which is 9. That's how many divisors it has. It doesn't tell you what any of them are. We know trivially that 2 of the divisors must be 1 and n, 1 and the number itself. It's a square number, so we know one of the divisors must be its square root as well. But for exercise, we are going to list the factors, or list the divisors of 100. And the answer is 1, 2, 4, 5, 10, 20, 25, 50, and 100. 125 is the third cube number, the fifth perfect cube. The number of divisors, 125, sigma sub 0, is simply 4. 1, 5, 25, and 125. 210, if I'm not mistaken, is a primorial. So it's 2 by 3 by 5 by 7. These are all first powers. And thus, to get sigma sub 0, it would be 2 times 2 times 2 times 2, or 2 to the 4, which is 16. And potentially as exercise, you could just list the first 8 divisors. So let's see, to do that mentally, okay, I'll try. 1, 2, 3, not 4. 1, 2, 3, 5. 1, 2, 3, 5. 6, 7. Hmm. 6, 7, and 10. And that's just halfway. So anyway, now to check and see if all of that is correct. So we get 4, 5, 8, 9, 6, 7, 10, 9, 4, and 16. Excellent. Greatest common divisor and lowest common multiple. GCD and LCM. Complementary concepts in number theory. Related in a very important way. That the product of the greatest common divisor of a pair of numbers with the lowest common multiple of that same pair of numbers is equal to the product of the numbers itself. E.g., don't pick a pair of numbers that are co-prime to each other. That's bad, because you know that their greatest common divisor is just going to be 1, so it's not going to work. So choose something like 12 and 18. Now we already know that 12 times 18 is 144 plus 72, so 216. What's the greatest common divisor of 12 and 18? The answer is 6. And what's the lowest common multiple of 12 and 18? The answer is 36. And indeed, 6 times 36 is 216. So now to find the greatest common divisor for these pairs of numbers by listing the divisors, by listing them. Okay, so for 12, we have 1, 2, 3, 4, 6, and 12. For 18, we have 1, 2, 3, 6, 9, and 18. And therefore, the greatest common divisor of 12 and 18, as stated above, is 6. It's the greatest common element in these two lists. But what's interesting to think about is, what if we just wanted a list of all common divisors of the pair of numbers? How many would exist? How many would exist? Could we create a short list from this pair of lists? In other words, can we just find their intersection, the size of their intersection? So for 30, we have 1, 2, 3, 5, 6, 10, 15, and 30. And for 45, we have 1, 3, 5, 9, 15, and 45. And therefore, their GCD is 15. For 14, we have 1, 2, 7, and 14. For 35, there's 1, 5, 7, and 35. And therefore, their GCD is 7, beg your pardon. And for 11, it's a prime number, so its only divisors are 1 and itself. And likewise for 19. And the greatest common divisor of any pair of primes is always 1, unless the two primes are equal, in which case it's the prime itself. And now, similarly, we are to find the lowest common multiple of a pair of numbers by listing multiples. But wait a minute, you can never run out of listing multiples. So what do? Maybe just list a few at a time and make sure that the lists sort of keep pace with each other. In this case, we already know ahead of time to go up to 24 because the numbers are so small. But in practice, I would just list the first 5 multiples perhaps. So 6, 12, 18, 24, and 30 with a comma. 8, 16, 24, 32, and 40 with a comma. And we notice 24 is the lowest common multiple on the list of multiples. So LCM of 6 and 8 equals 24. Now for 10 and 12, we think, won't all the elements of the multiples of 10 just end in a 0? So wouldn't it cut down on my workload, and shouldn't I just list the multiples of 12 until I hit one that ends in a 0? And that's correct. So 12, 24, 36, 48, and 60. And it must be 60. So the lowest common multiple of 10 and 12 is 60. For 5 and 9, we have a similar thought. We know a divisibility rule for 5 is that if the number ends in 5, it's divisible by 5. Or if it ends in 0. So I just have to go forward in the 9 times table and wait until I hit a number that ends in 5 or 0. And I don't have to list out the multiples of 5. So 9, 18, 27, 36, and 45 is the answer. For 20 and 30, wait, isn't this basically the same as doing it for 2 and 3? Except everything is 10 times bigger. Everything just has a 0 on the end. And that is indeed right. And for the lowest common in 3, you should just know straight away that it's 6. So in this case, it would not be 6, but 60. And we make sure that everything is correct. Okay, that's all good. That's all good. Use the prime factorizations to find the greatest common divisor and lowest common multiple of the pair of numbers. So you don't have to actually find out what these numbers are in particular. We can see that B would be 2 times 9 times 5, which is 90. But you don't have to figure that out. And indeed, for something like this, it would be a bit of work. It is sufficient to have the numbers in their prime factorized forms. To find the of A and B when they are in this format, list all the primes in the base position that you can see. So I see a 2, a 3, and a 5. Then you're looking for a number that is smaller than A and B. It has to be, because it's a divisor, right? So look for who has the smallest power of each number one by one. So who's got the smallest power of 2? The answer is B. And what is its power of 2? The answer is 1. Who's got the smallest power of 3? The answer is A. And what is its power? The answer is 1. Who's got the smallest power of 5? The answer is B. And what power of 5? The answer is 1. So we multiply these together and we'll get the answer. And the answer is 2 times 3 times 5, which is, of course, 30. For the lowest common multiple, it's pretty much the same thing, but in reverse. You start out just the same. You list the 2, the 3, and the 5, because those are the prime numbers in the base position that you can actually see. And then you just say, not who has the lowest power of 2, but who has the highest power of 2. In this case, it's A. And what power of 2 do they have? The answer is 3. Who's got the highest power of 3? That would be B. And its power of 3 is 2. Okay, who's got the highest power of 5? The answer is A. And what power of 5 is it? The answer is 2. So now, if you actually go ahead and compute this, you will have obtained the lowest common multiple of A and B. I want to compute it just because I like doing so, but you don't actually have to. I don't think so anyway. So let's see. 8 times 25 is 200, and 200 times 9 is 1,800. And I'm curious what the original numbers were in the first place. So we already know that B is 90. As for A, that would be 8 times 3 times 25. Well, 8 times 25 is 200, and 200 times 3 is 600. So these were the original numbers. And therefore, these answers look correct. They look correct. We don't know if they are correct, but they look correct. Okay, let's play the same game now with C and D. Which prime numbers do I actually see in the base position? Well, I see a 2, and I see a 3, and I see a 7. Okay, so just write down 2, 3, and 7. And now you have to find out what powers 2, 3, and 7 actually have. So who has the lowest power of 2? It would be this guy. So I put a 1 there. Who has the lowest power of 7? It would be this guy. C. It would be C, and it has 1. Okay. Who has the lowest power of 3, though? Would it be this number D right here? 3 to the 1? No. It's actually this number over here. But I don't see any 3 there. I know. There is a secret, invisible 3 inside there. You just can't see it. It's 3 to the power of 0, which you know is secretly 1. So what should I put as my power of 3 then? The answer is 0. And that's your answer. We compute it, we get the number 14. LCM is the opposite game. Write down the 2, the 3, and the 7, and then ask yourself, who has the highest power of each? For 2, it would be this one, 2 to the 2. For 3, it would be this one, 3 to the 1. And for 7, it would be this one, 7 to the 2. And now compute. 3 times 7 squared is 147. 147 times 4. Well, if I double it, I get 294. And if I double that, I get 588. And that's your answer. Out of curiosity, I'm going to compute C and D, but you don't actually have to. So this is 4 times 7, huh? So that would be 28. And this is 2 times 3 times, 2 times 3 times 49. So that's 6 times 49, which is the same as 6 times 50 minus 6, which is 294. So these answers seem correct. Okay, let's see. The GCD of E and F. What prime numbers do I actually see in the base position? Well, I see a 2, a 3, a 5, and an 11. But did you notice that E and F have no prime bases in common? F has 2 and 3, and E has 5 and 11. They have nothing in common. So when we play the game of like who's got the lowest power of whatever prime factor, it's always going to be 0. It's always going to be 0. To really stress my point and to make it explicit, I would just end up with this as a result. Not very interesting, right? So that would be a bunch of 1s multiplied together. So the answer is 1. These numbers, their greatest common divisor is simply 1. And that means that E and F are coprime. They look at each other and they think, oh, you look like a prime number to me. Oh, yeah, well, you look like a prime number to me. Of course, they're not really prime numbers, but they look like primes to each other. They have no common divisors at all except for 1. Okay, as for LCM, we write down 2, 3, 5, 11. Now, because of that theorem from earlier, which says that GCD of A comma B times LCM of A comma B is A times B, as we have already established that the GCD of the pair of numbers in question is 1, then their lowest common multiple must simply be equal to their product. It has to be. If the numbers are coprime, then their lowest common multiple is their product. A special case of this is when the numbers are literally a pair of prime numbers. Okay, so what that means is the LCM of E comma F is 2 squared times 3 to the 1 times 5 to the 3 times 11 to the 1. So what if I did want to actually compute this? What I would do is I would recognize that I can break it up into 2 squared times 5 squared, which is 100, with a spare 5 left over. And that's a 3, and that's an 11. So it doesn't look so bad when it's like this, right? Because 5 times 11 is 15. Sorry, beg your pardon. 5 times 3 is 15. And 15 times 11 is 165. So just write 165 and stick 2 zeros on the end. And that's the answer. Of course, possibly for completeness sake, I just really want to know what these numbers actually are. So F is, of course, 12. And E is 125 times 11, which is 1375. So it looks right. Okay, and lastly here, we have to compute the GCD of G and H, and then their LCM. All the prime factors I can see in the base position. In both cases, it's 3 and 5. So who has the lowest power of 3 and the lowest power of 5? In this case, it's a 2 and a 1. And what about the highest power of 3 and the highest power of 5? In this case, it's a 3 and a 1. And we compute, and we get 45. And 27 times 5, which is 135. And when we compute the numbers themselves, because of course you would notice that this actually is H, and this here is G. So we get this. So special theorems apply, and special cases apply in computing the GCD and LCM when one number is a multiple of the other. In this case, it was equivalent to me computing the GCD of G and 3G, and the LCM of G and 3, and the LCM of G and 3G. Okay, now to find the GCD and LCM for these numbers. But I guess they want us to find the factorization first. Very well. For 50, it would be 2 times 5 squared. And for 60, it would be 2 squared times 3 times 5. For the greatest common divisor, we could go through the whole sequence of writing down 2, 3, and 5 and playing that sort of game. But when the numbers are this sort of small, we don't have to be so careful, and we can actually just look at their prime factorizations. So in this case, it would be 2 times 5, which is 10, which is what we thought so in the first place. And for the LCM, 2 squared times 3 times 5 squared. So that's 12 times 25, which is 300. Just like if I were computing the GCD and LCM of just plain old 5 and 6, but with a 0 on the end of my results. Prime factorizations now of 42 and 98. For 42, it would be 2 times 3 times 7. And for 98, it's 2 times 7 squared. We compute the GCD and LCM of this pair now. For the GCD, it would just be 2 times 7, which is 14. And for the LCM, it would be 2 times 3 times 7 squared, which is 6 times 49, which is the same as 6 times 50 minus 6, which is 294. For 24 and 54, 24 is 2 cubed times 3, and 54 is 2 times 3 cubed. The GCD of 24 and 54, that would just be 2 times 3, wouldn't it? Which is 6. And for the LCM of 24 and 54, that would be 2 cubed times 3 cubed, which is the same as 8 times 27, which is 4 times 54, which is 216. But we also notice that it's the cube of 6. And now for 16, 120, well, that's 2 times 5 times 2 squared times 3. So 2 cubed times 3 times 5, just like that. And now their GCD and LCM. The GCD would be 2 cubed, which is 8. The LCM would be 2 to the 4 times 3 times 5. So just 2 times this, 240. And now we check. Everything must be checked. Okay, 1 and 2 are correct. 3 is correct. Oh, so is 4 and 5, and 6, and 7, and 8. All good. All good. Okay. Now comes the Euclidean algorithm. What on earth is that? It's a way to find the greatest common divisor of a pair of numbers, and it's quite an elegant algorithm. So I think it's better if I just sort of do the steps in the first place, just seeing how large the numbers are relative to one another. So we already know a divisor of 60 and 24 is 12, but we'll use the Euclidean algorithm to get used to it. So 64, but what? 60, beg your pardon. Now, something and get the remainder. Well, I've seen different ways to write it. I've seen mod, and I've even seen the percentage sign. So what I'm going to use is I'm going to use mod. So 60 mod 24, that would be 12. And then 24 mod 12 is 0. And it's the last non-zero number that you get from doing this process. And so the answer is 12. And we try here. 110 mod 45 is 20. 45 mod 20 is 5. 20 mod 5 is 0. And the last non-zero answer is 5. And that's our answer. So we, wait, is that actually true though? Hold on. Oh, yes, it is. Okay, great. So now 98 and 56, but wait a second. What is the... I want to make sure that I'm not forming a bad habit, and I'm investigating what is the most widely accepted notation for this. And this is an instance of a valid use of an LLM because it's trained on many diverse sources, and it's designed to like be as average and representative as possible. So if I'm asking it what is the most widely accepted something, it's going to give me like the most standard answer. Like it's designed to be boring and predictable, and you know what. So anyway, okay, do I really have to write that every single darn time? Okay. Yeah, they write it like I do. They don't write the three bars. 7 is congruent to 1 modulo 3. I know, but they don't actually write that. Unless it's like for an identity or something. You know what? I'll try it out. Whatever, I'll try it out. Okay, so 98 and 56. The remainder would be 42. Okay, so I guess I have to write this. All right, so now for 56 and 42, well, that would be 14. So 56 is congruent to 14 modulo 42. All right, and for 42, do I just write this? I better check. Wait. Okay, they would. I prefer the first way of writing it, but I'm going to try this way so that I get more used to something different. Okay. I just have to remember to put the numbers in the correct order. 7 is congruent to 1 modulo 3. 7 is congruent to 1 modulo 3. 7 is congruent to 1 modulo 3. All right, I'll try it. 255 is congruent to 45 modulo 105. Right? Oh, yes, it is. Okay. 45. Well, it would be 15. So 45 is congruent to. No, 105 is congruent to 15 modulo 45. 45 is congruent to 0 modulo 15. And thus the answer is 15. And up here, the answer is 14 times table. The answer is just 17. There's no need to do this. But wait, maybe there actually is a need. Right? Anyway, the greatest common divisor 15 matches that. Where's the answer of 17 then? Okay, so I guess this teaches me the importance of paying cases, because look, where is the answer of 17? So up here, I mean, I guess you just say 17 and you just declare it from the outset. That's what I'll do. $88 is congruent to 4 modulo 21. 21 is congruent to modulo 4. And of course, 4 is congruent to 0 modulo 1. So the GCD of 88 and 21 is just simply 1. They are co-prime. Yes, that's what this implies. That's fine. 198. $198 doubled is 396. And so there is a gap of 30. So 432 is congruent to 36 modulo 198. Is 180. So 198 is congruent to 18 modulo 36. And finally, 36 is congruent to 0 modulo 18. And so the final answer is 18. And now for 1111. 111 has 999 as a multiple. But I guess that won't help me too much. No, it will. It will accelerate it rapidly, actually. So 1000 is congruent to 1 modulo 111. 111 is congruent to 0 modulo 1. And so the GCD of these numbers is 1, and so they are co-prime. And now we must check. Everything must be checked. Everything must be checked. So I see that's the way they give their answer. Right, so it's the last one. I will show you like this. I actually quite like that. Yeah, I can see why that's quite okay actually. So anyway, everything must be checked. 12 for the first one, that's correct. Then 5. Okay, so it's the list. Then 14, then 15, that's all correct. 17 is fine. Then 1, 18, and 1, and that matters. Okay, so I'm glad practiced that alternative notation before, because now it looks like there's some of that here. Evaluate each expression and the remainder. So I know that the answer is simply 1, but I'm curious how they would like it to be presented. So I'll just scroll down just a little bit. Okay, so they really do just want the final answer. So for here, the answer is 1 because 5 times 4 is 20, and so we have 1 remaining. For here, the answer is 2 because 8 times 6 is 48. So there's 2 left over. 100 divided by 13 is 7, remainder 9. So the answer is 9. Now, what do I do here? Because it's larger than 12. Well, 12 divided by 15 is 0, remainder 12. So the answer is 12. And here, of course, 30 is on the 10 times table. But what about here? I'm going to bet that the answer is -5, but I could be completely wrong. Perhaps they standard. No, you know what? I'm going to bet the answer is 2. I actually think that might work, but I don't know. I really don't know. And I guess this underscores the importance of definitions. So instead of looking at the answers, I'm going to ask this LLM Gemini. I'm going to ask it a similar question, but not the same one. So let's see. What is -10 mod 3? No, mod 7. I'll ask it, what is -10 mod 7? And I'll ask another LLM, and if they agree, okay, that gives me some confidence in the answer. Okay, so Claude says 4, and so does Gemini. And so that aligns with my thinking. So I think the answer is 2. Okay. And for this, I think the answer is 9. And now I must compute 33 and 15. 33 add 15, which is 48. And 48 divided by 9 is 5 remainder 3. So I will say 3. 100 minus 10 is 90. And 90 divided by 11 is 8 remainder 2. So I shall say 2. 5 times 7 is 35, and 35 divided by 6 is 5 remainder 5. So I will say 5. 12 times 12 is 144, and divide that by 5, and you get 28 remainder 4. So I will say 4. 3 cubed is 27, and 27 divided by 4 is 6 remainder 3. So I will say 3. 2 to the 5 is 32. 32 divided by 7 is 4 remainder 4, so I will say 4. And 10 cubed is 1000. 1000 divided by 9 is 111 remainder 1, so I will say 1. And everything must be checked. Everything must be checked. Okay, the first 3 answers are correct. So are the next 3. And so are the next 3. And so are the remaining ones. Okay, solving linear congruences. Find the smallest positive integer x that solves each equation. So we are looking for a number which, when you add 3 to it, and then divide the result by 5, you obtain a remainder of 1. So working backwards, what can you divide by 5 and obtain a remainder of 1 from? The answer is 6, 11, 16, 21, 26, and so on. And they want the smallest positive integer which satisfies that. So I believe that the answer is 3. Because 3 plus 3 equals 6, and 6 divided by 5 is 1, remainder 1. Oh, there's a tiny insect of some kind. They want a number which, when you add 10 to it and divide the result by 12, you obtain a remainder of 7. So how does this? So I guess I should just look at these numbers here and just think of the 12 times table plus 7. The 12 times table shifted to the right by 7. So what, 1931, 43, 55, and so on. I guess that's how this works. And they want the number. Is the answer simply the first one for this one to get the smallest? Okay, so first, oh no, whoops, nearly saw the answers. So, all right. A number which, when you subtract 5, gives you 2 after dividing it by 8. So what are the numbers that are congruent to the positive numbers which are congruent to 2 modulo 8? Right. And then the smallest positive number which has this property, when I subtract 5 from it, I get that. So wouldn't the answer just be 7? I suppose. Try this out. So 6, 15, 24, 33, 42, 51. And it's the number from which I subtract 1. So would it be 7 again? Okay. And now I'm congruent to 1 modulo 3. So that would be 1, 4, 7, 10, 13, 16, 19, 22, and so on. Now, which is the smallest one which is even? The answer is 4. And so would x simply be 2? And now I will try this. So 1, 6, 11, 16, 21, 26, and so on. And which is the smallest one that is a multiple of 3? And the answer is 6. And so would the answer be 2 again? Now, in case I'm getting this completely wrong, I need to check 3 at least. The answers to the first 3. So that's good. Which number 3 modulo 7? So that would be 3, 10, 17, 24, 31, 38, and so on. And which of these is a multiple of 4? 24. And it's the 6th multiple of 4. So the answer is 6. Okay. 2, 13, 24, 35, 46, 57, and so on. And that's the first multiple of 5, and it's the 7th multiple of 5. So that's good. 4, 14, 24. Which is a multiple of 2? Well, it would be this one. And so is the answer just 2? And last, those numbers congruent to 5 modulo 15. Uh, 5, 20, 35, 50, 65, 80. And which is the lowest multiple of 10 in this set? The answer is 20, and it's the second multiple of 10. So now to answers. Okay, so the first 3 are correct. And so are the next 3. And so are the last. Wonder what is the actual technique to... I don't know. So I'll have to see. What would a good candidate? Oh, really? So you just... It's just like solving a standard linear equation. You just subtract 10 from both sides, you would get -3, and then you do modulo 12, so you get 9. I didn't know this. Okay, so who is next? Linear Diophantine equations. Have dinner. So be well, be well.